Hello, welcome. Hi, in this video we are going to discuss some important concepts in topology that is very closely related to the Brewer fixed point theorem and related results. We recall that the fixed point of a given function f which is defined from x to x, where x is a space, into itself is a point x, small x, in capital X, for which f of x equal to x. That means the function value of that point will be coinciding with the same point, so will give the same point as the answer. So a space X has the fixed point property. When do we say that a space X has the fixed point property? Provided that every continuous function f defined from x to x, if every continuous function f defined from x to x has at least one fixed point, then we say that the space X has the fixed point property. Now we are going to see a result which states that S1 is not contractible. The space X S1 is not contractible. How can we prove this? It's a very simple proof. A simple proof is available for this result. The unit circle S1 is not contractible. So we have we know that every contractible space is simply connected. We have seen that we have proved that every contractible space is simply connected. But for a simply connected space, its fundamental group is the trivial group. It contains only one element, that is the identity element. Only one element is contained in the in the fundamental group of every contractible space, or every simply connected spaces, and also every contractible space is simply connected. And therefore, if S1 is contractible, and then it must be simply connected. If S1 is contractible, it must be simply connected, and if it is simply connected, then its fundamental group must be isomorphic to the trivial group. But actually, S1, it's the fundamental group. We have proved that the fundamental group of S1 is isomorphic to Z, is the additive group of integers. That is, pi1 of S1 is isomorphic to Z. And therefore, thus both these statements cannot go together, and thus we get a contradiction. Therefore, S1 is not contractible. So we have to make the correction that if we proceed correction to the situation that we created here by proceeding just by assuming that S1 is contractible, and that's why we got that contradiction. So S1 is not contractible. Next, we have a definition, an important definition. In this definition, we are going to see a continuous function f, which can be that continuous function can be called a contraction, and the resulting space can be called it's a retraction, not a contraction. It's a retraction. The continuous function can be called a retraction, and the resulting space can be called a retract. So for that, let A be a topological space, that's a subspace of a given space X. Let X be a given topological space, and let A be a subspace of that given space. And we say that A is a retract of we can say that A is a retract of X, provided that there is a continuous function f from X to A. If it is possible to find, if it is possible to define a continuous function from X to A, for which f of A equal to A for each element A in A. For each A in A, if f of A equal to A, that means the function f, the continuous function f, fixes every point of A. The function f is then called a retraction, and the subspace A is called the retract of the space X. We can see some. We have some examples given here. Let's discuss these some examples. The first case, first example. See, we consider an annulus. In an annulus, we know that it has annulus has two boundaries, and the outer boundary is a circle, inner boundary is also a circle, and that annulus can be taken equal to a. That annulus contains the points x1, x2, which are members of R2, such that a square is less than or equal to x1 square plus x2 square is less than or equal to b square. So the inner circle, in this annulus we can take that inner circle separately. The inner circle has the equation d equal to x1 square plus x2 square equal to a square, as a is the smaller is smaller than b. So the inner circle is x1 square plus x2 square equal to a square. And we also know that we have proved that it's a deformation retract of a. That inner circle is a deformation. Moreover, the outer circle is also deformation retract of a. We also know that every interior circles, which is concentric to any circle which has the same radius, can be a deformation retract, and that we know. But here we are restricting our attention to only the inner circle. Then we can give a continuous function, or we can choose a continuous function, and that is the deformation retraction. There exists a deformation retraction. It's because D is a deformation retract of the space A. So there must exist a deformation retraction H, which is defined from A cross I to A, with the property that H of x0 equal to x, and H of x1 is an element of D for all x belonging to A, and hy of t equal to y, where y is an element of D for the points y belonging to D. And also t belongs to a. T is an element of I. Now we can define the function, a continuous function h. H can be defined from a to d. We define h from a to d by h of x is equal to h of x comma 1. With the help of that deformation retraction, we define a continuous function h. Since h is continuous, small h must be continuous. The newly defined function must be continuous. And also for a belonging to D, if a is an element of the subspace D, then h of a equal to h capital H of a comma 1 equal to a, and therefore h is a retraction. Thus h is a retraction, and hence it is clear that the subspace D is a retract of the given space A. And we can also say that it's the one level of, actually it is the one level of the deformation retraction from which is defined from A to D. And thus now it is clear that for every deformation retraction that exists from a given space to its subspace, we can define a retraction actually. So every deformation retraction can give rise to, can give us a retraction. And so deformation retract can also be converted into or can also be accepted as a retract. So every deformation retraction can give us a retraction. So every deformation retract is a subspace. So retract can give us a retract. Now see here in the second example. Here we consider the closed subinterval CD of the big subinterval AB. So CD, the closed subinterval CD, is a subset of it's a subspace of the big subinterval AD, closed interval AB. And then it's a retract of AB. We can prove that the subinterval, closed subinterval, is a retract of the big subinterval closed interval AB. The third example, see here it's a different case. It's not given as an example. It gives us a case which is not a retract. It tells us about a situation where we do not have a retract. So the set of the endpoints of we consider for that the set of endpoints of the closed interval AB, that is capital A equal to set AB, it's a subset of the given interval AB, closed interval AB, but it is not a retractor of the closed interval AB, where A is less than B. It's because the closed interval AB is connected. See, the closed interval AB is connected, but A is not. See, it is not a. But the set A is not a connected set. It's a disconnected set. Okay, now in order to before closing this video, we have one more situation to discuss. Every deformation retract. See, every deformation retract can give us a can give us a retract. Every deformation retract can give us a retract. And also deformation retraction or a retraction can be obtained from a deformation retraction. A retraction can be obtained from a deformation retraction. So a deformation retraction can always ensure that there exists a retraction. Actually, a retraction can be some in that situation. If there exists a deformation retraction, then the retraction obtained from that deformation retraction can easily be seen as the one level of that deformation retraction. Or if we take the one level of the deformation retraction, we get a retraction. Or once again, if we take the one level of a deformation retraction, we are going to get a retraction. But the conveys may not be true. Given a retraction, see, what is the conveys? Given a retraction, is it possible to show that there exists a deformation retraction such that the given retraction is the one level of that deformation retraction? Actually, it is not possible. To prove this, we can consider the case of S1 and the single point in a point which is present in S1. You consider S1 and a point which is present in S1. We can define a function f from S1 to, and let's take, for convenience, let's take the point, a single point as x0. So we can define the space, subspace D is equal to set x0, where x0 is in S1, and we can define a function f. It's a continuous function. We can be defined as a continuous function f from s1 to x0, such that f of x equal to x0, f of x equal to x0 for each x in s1. See, for each x in s1, we define we associate that image to the single point x0. So f of x is equal to x0 for each x belonging to s1, and then this function is a constant function, or so it's a continuous function. But this continuous function, it cannot be developed into a deformation retraction, a retraction using this, or in other words, we cannot develop a deformation retraction using this continuous function or using this retract. So if there exists a deformation retraction from S1 to the single point x0, then we have to say that the single point x0 is a retract of we have to say that so actually x0 is a retract, but it is not a deformation retraction. If there were existing a deformation retraction from S1 to the single point x0, then we have to call that the subspace x0 as a deformation retract of the space x1, and that will contradict the fact that pi1 of x0 is the trivial group, which contains only the element 0, and the fundamental group of S1, and that is Z, and both are isomorphic. Then that will lead to, and this the steps that we have adopted will lead to the conclusion that the trivial group is isomorphic to that group Z of the additive group Z of integers. So that's actually thus we are going to get a contradiction. That means in short we can say that we are going to get a contradiction here if we proceed in that way. So we have to say that we have to correct that there cannot exist yeah, actually we have to accept that there cannot exist we cannot develop a deformation retraction, a deformation retraction from from all retraction actually which exists from a given space to its subspace. Okay, therefore the conveys is not true. But the statement that every deformation retraction can give us a retraction is correct. But the statement that every retraction can give us a deformation retraction, every retraction can give us a deformation retraction is wrong. And that is the conveys, and this conveys is not correct. So that's all. Thank you for listening.